Dear students, good morning. In the previous videos, the last video, we completed the second exercise and started the matrix transpose. That is a transpose of a given matrix. With some examples, it is completed that concept. Now, the very important two concepts are there. Already I wrote on the board. Okay, now you see, these are the two definitions. These definitions are also asked in the previous exams. 2 marks question. You see, symmetric matrix and skew-symmetric matrix. Symmetric matrix and skew-symmetric matrix. There are two concepts. This is a matrix chapter, 10th part. Okay. The symmetric matrix. What is the symmetric matrix means? First of all, that matrix A is a square matrix. You note it well. A square matrix, capital A, with the condition A is equal to A transpose. That square matrix A is a transpose of itself. A transpose is equal to A. That is the condition. Then that square matrix A is said to be called as a symmetric matrix. Okay, now? Right. Generally, we will take, it is also included in the definition. If capital A is equal to Aij, capital A is a notation for matrix, small aij, ith row, jth column. Small aij is a gender element in the matrix. It is not m by n, it is n by n only, because it is a square matrix. N rows, n columns. And its transpose is Aji, not Ij, Aji. Transpose is there. But order of the matrix is same, n by n. If they are equal by the condition, with the condition A is equal to A transpose, that matrix A is said to be called as a symmetric matrix. So here A is equal to A transpose. That means box Aj is equal to Aji. For all Aij is equal to Aji. These are the elements. The positions are same. Will be changed. The positions are different, but the element are same. Then one example. Here the 2, here also is 2. Okay now? Here in this matrix capital A is this 2 is first row second column, whereas this 2 is second row first column. Aij, Aji. You can understand it. But these are different. In the diagonal, the elements are different elements. Because the diagonal elements is A11, A22. It will not be changed. Okay now. Here in this case, if capital A is equal to 1, 2, 2, 0, its transpose is first row will be changed as a first column. Second row is changed as a second column. 1, 2, 2, 0. It is nothing but again A. Okay na? Here A is equal to A transpose. That is why the condition is satisfied. Here capital A is called as a symmetric matrix. It is a symmetric matrix. Okay, Nana? Yeah. One more example. Capital A is here it is 3 by 3 matrix. I am taking a 3 by 3 matrix. You see 1, 6, 7, 6, 0, 8, 7, 8, 9. If you change it, transpose it, then A transpose is equal to the first row will become as a first column. Second row is a second column. Third row is a third column. Okay now, you see here the 6 and the 6 is same. 7 is same. 8 is same. Okay now, that is, you try to understand. Here in this 6 is, its position is first row second column. But here second row first column. Aij, Aji. Okay now. Or otherwise, if you transpose it, this is nothing but that A 167 Okay, na? Same 167 is there. 167. Here also 167. Same matrix capital A. If you transpose it, again we get the same matrix A. So here A is equal to A transpose. A power T is written, A dash or otherwise A power T. That means A transpose. Here A is equal to A transpose. That implies A is a symmetric matrix. Two examples. Okay, now? Very simple. Symmetric matrix is a square matrix and it is equal to its transpose. Capital A is a symmetric matrix when it is with the condition A is equal to A transpose. Okay, now? Like that you have to by heart. If you simply define the square symmetric matrix, you have to write this one and write the example also. Okay, now? Is it clear? Now we come to second one. It is a skew-symmetric matrix. SKEW, skew, some hyphen is there. Symmetric matrix. Okay, now, if A is a square matrix, similar, A is a square matrix, and if A is equal to minus A transpose, then A is simply A transpose. But here A is equal to minus A transpose. Some sign is changed. Minus is there. Then A is said to be called as a symmetric matrix. Will you agree? Yeah. Here also are taking generally capital A. Capital A means it is a matrix rotation. Aij is a general element. N by N is a square matrix. So N rows, N columns. A transpose is Aji, N by N one. If A is equal to minus A transpose, condition is there. Aij minus Aji. Okay, now? If you send it minus Aji N by N, will you agree now? Minus means minus 1, just like a K constant. That multiplies all the elements included in that box. So it goes inside, minus Aji. For all, these two matrices are equal. So Aij here, it is minus Aji. Okay, now? Then A is called as a symmetric matrix. Okay, now? Up to this one you have to mention, you have to write. Whenever you ask this question as a 2-mark question, define the skew-symmetric matrix with some example also. It is a general. Here one more thing is very important. If I is equal to J, when I is equal to J, Aii, A11, A22, A33, you see, this is A11, first row, first column. This is A22, this is A33. Will you agree? So I is equal to J means that the elements in the diagonal. If I is equal to J in this case, what will be happen? Aii minus Aii only. J is equal to I. Here J is equal to I. Okay, now the same element is repeated. So it comes to this side. Aii plus Aii. Same repeated. It is 2 Aii. Will you agree? Don't confuse. The suffix I means its position. Ith row, ith column. First row, first column. Second row, second column. Those elements are lying in the diagonal. 2Ii is equal to 0. 2 comes to this side, 0 by 2 is 0. So Aii is equal to 0 for all i's. For all i's. I means I may be 1, 2, 3 up to n. Because n by n is general. Okay, now? That means all elements in the diagonal are zeros. Okay, now? You see that? 0, 5, minus 5, 0. You see here, in the diagonal, zeros are there. What is A transpose? This first row become as first column. Second row become as second column. Okay, now? Here is A transpose. If you take minus as common, 0, minus 0 is simply 0. Here minus 5. Minus comes out, so it is 5. Here it is plus 5. Minus of minus 5 is there. You see, you sent minus 2, minus into minus plus 5 only. Minus into 0, 0 only. Minus into 5, minus 5. So I am taking minus as common. Then this will become as A. This is minus A. So A transpose is minus A. That means A is equal to minus A transpose. Both are same. You see, A transpose is minus A. A transpose, we proved A transpose is minus A. That means minus A is equal to A transpose. A is equal to minus A transpose. You write it like that only. Minus. You send this side. A is equal to minus A transpose. Like this. So A is equal to minus A transpose. By the given condition, here condition is there. So A is a symmetric matrix. Okay na? You go through it 1 or 2 times. Okay na? It is only one example is given. Again, so many examples are there and exercises are there. We can follow it. You can go through that one. First of all, you try to understand what is symmetric and skew-symmetric. Once again, A is equal to A transpose. That is symmetric. Very simple. Here A is equal to minus A transpose. Okay na? These are the two different definitions. Try to understand. Okay na? Yes. Yeah. One more example for skew-symmetric. Suppose capital A is equal to 0 G H G 0 F. It is H F 0. Okay na? But it is minus. You see that? Suppose it is a given matrix A, which is 3 by 3, is a square matrix. Then what about A transpose? A transpose means these elements, first row elements, will become as first column. Second row elements will become as second column. And this is HF 0. Will you agree? Okay now? If you take minus, that is to be noted well. If you take minus 0 is 0. This is minus, this is minus H. Here is minus is come out, it is G1. It is 0. It is minus. If minus is come out, it is H. Here it is F and it is 0. Okay now? Here is nothing but minus. This is same as A. Will you agree? So this is A. That means we take A transpose and we prove that minus A. That implies, you see, A is equal to A transpose. That implies A is what is A? If this condition is satisfied, A is a skew-symmetric. It is a skew-symmetric. Okay na? It is a skew-symmetric. Okay na? Like it. It is one more example. Okay na? Now, observe. Okay, 2 definitions and some examples are given. Right, now a theorem, it is an important theorem. It is also asked in the previous exams. It is dated. Dated means previously asked. You see, the question statement is, for any square matrix capital A with real entries means real elements. The elements must be real number, not imaginary, only real. Then A plus A transpose is a square matrix, is a symmetric matrix. Whereas A minus A transpose is a skew-symmetric. Fantastic concept. A plus A transpose is a symmetric matrix. Whereas A minus A transpose is a skew-symmetric matrix. We have to prove. That means any matrix, any square matrix whose elements are real numbers, okay, you leave this one. Any square matrix, if it is added with its symmetric, it's transpose. Any square matrix is added with its transpose, that is A transpose. A plus A transpose. Then that will become as a symmetric matrix. Any matrix A is added the minus A transpose, or the difference of matrix, any matrix A and its transpose. That means this one, A minus A transpose. It will become as a skew-symmetric. We can prove. You see, proof. Let B is equal to, B is a matrix, we assume. It is A plus A transpose. For any matrix capital A, we are taking a matrix A plus A transpose. That matrix, taken matrix A is added with its transpose. If it is, it's a sum, not difference. The sum, let it be capital B. Now, we are making transpose on both sides. B transpose is equal to A plus A transpose whole transpose. Will you agree? We are considering A plus A transpose as B, and we are making transpose on both sides. Here transpose is one application. Adding 2 on both sides, making a difference 2 on both sides, multiplying with k, dividing with k, squaring on both sides, just like making a transpose on both sides. It is also an application. Then this is B transpose simply. But yesterday I taught a property like that. It is A transpose plus A transpose whole transpose. Okay na? A property is there. Yesterday it is a proofless property. A plus B whole transpose means A transpose plus B transpose. Okay na? It is a property. Like that A transpose whole transpose. A transpose plus transpose whole transpose is nothing but A dash whole power dash. Yesterday I used dash, here T transpose, both are same. So A dash whole dash means A transpose whole transpose is simply A. That is nothing but A plus A transpose. That is nothing but B. What we consider, that same thing will come. So B transpose is equal to B. That implies B is a symmetric, okay na, symmetric matrix. How can we say any matrix is equal to its transpose? Then it is called as a symmetric matrix. B is symmetric by this one. B is good. B transpose means B is a symmetric by definition. What is B? What is B? A plus A transpose. B means A plus A transpose is a symmetric, okay na, a symmetric matrix. Okay na? So the first part is over. Suppose A is any matrix whose elements are real, then we consider A plus A transpose just like A, and we prove that A B transpose is equal to B, so that B is a symmetric matrix. B means A plus A transpose is a symmetric. Is it clear? So any matrix, if it is added with its transpose, the sum of any matrix and its transpose is a symmetric matrix. Okay na? Right. Now Right, another one. The second part. Let capital C is equal to A minus A transpose. Here also same. A is any matrix. Now we are making a transpose on both sides. A minus A transpose whole transpose. Here it is simply C transpose. Okay now? Here also it is A transpose minus A transpose whole transpose. It is A transpose minus A1. You know this condition. A dash whole dash. The last video we prove with taking one example also. A dash whole dash is A. A transpose whole transpose is A1. This is minus of A minus A transpose. Will you agree? I am taking minus as common. It is minus A transpose is nothing but C. Our data is taken, we are considering like that one. So C transpose is nothing but C. That implies C is equal to minus C transpose. What is the definition? If C is a matrix, it is equal to the negative of its transpose. So that implies C is a skew-symmetric. It is a skew-symmetric matrix. Okay, now it is a skew-symmetric matrix. Try to understand it. C is equal to minus C power T, C transpose. That is skew-symmetric it is. What is C? It is A minus A transpose is a skew-symmetric. Okay, now skew-symmetric matrix. Will you agree? Yeah. So that is the first part and is the second part. Any matrix, the sum of any matrix, square matrix with its transpose is a square matrix, is a symmetric matrix. Whereas the difference of any matrix by its transpose is a skew-symmetric matrix. Okay, Nina? Like this, I have to prove. That is important theorem. Yeah. Yeah, okay. This is theorem 2. Any square matrix, the statement I am reading. Any square matrix can be expressed as the sum of symmetric, this is a sum of symmetric and skew-symmetric matrices. Okay now? That is one statement. Any square matrix, capital A, it can be expressed as the sum of symmetric and skew-symmetric matrix. Any matrix. It's a very good concept. Observe me. The proof is needed. It is also a dated problem. Try to understand. Let capital A be any square matrix. It is any square matrix, suppose we take A. And we have to prove that that A can be expressed as P plus Q. Just like where P is a symmetric and Q is a skew-symmetric, we have to prove that. You see, some logic is there. A is equal to, can you write 1 by 2 into 2A? Can you write? Yeah. We are multiplying with 2 and dividing with 2. It is 1 by 2. It can be A plus A. Will you agree? 2A. It is 1 by 2. A plus A transpose plus A minus A transpose. Just the A itself, a square matrix taken, consider square matrix. It is an arbitrary square matrix, any chosen matrix, selected matrix. That can be logically multiplying with 2 and dividing with 2. That 2A is A plus A. And here also A plus A is there. We are adding A transpose and subtracting A transpose. No change at all. It is 1 by 2 A plus A transpose and 1 by 2 A minus A transpose. Will you agree? Okay now. A plus A transpose means actually A plus A transpose is a symmetric. Okay na? Symmetric matrix. Okay na? And here also 1 by 2. Already we solved in the previous definitions. A plus A transpose. The sum of matrix and its transpose is a symmetric. The difference of a matrix with its transpose is skew-symmetric. We know it well. Skew-symmetric. Okay na? Skew-symmetric matrix. Okay na? In the previous definition, in the symmetric matrix, suppose A is a matrix. Then A dash or A power T, that is A transpose. A dash is its transpose. You see that? Suppose K transpose is K into A transpose. K A whole dash is equal to K A dash. We know this condition. Okay now, like this, here 1 by 2 is just like a K. If you send into inside, again it is a symmetric matrix. Try to understand. It is also symmetric. Okay now. So again we may write it as a symmetric matrix. Okay now. That the constant enters in by using that condition. Okay now. Don't confuse. You see, again I will tell it. 1 by 2 into again a matrix. 1 by 2 plus A transpose. Again A transpose. Same. No need to worry. This 1 by 2 is just like a K. A constant. Okay now. So we get the 1 by 2 of any symmetric matrix. The multiplication of symmetric matrix by any constant is again a symmetric matrix. Simply you take it. Symmetric matrix is there. We are multiplying with a constant. Again the resultant matrix is also a symmetric matrix by using that one. Here also you see it is a skew-symmetric. Here also the same condition will be repeated. Okay now. So now you see it is symmetric and it is skew-symmetric. Their sum is a yeah. Will you agree now? So the sum of symmetric and skew-symmetric is a given matrix. So A is any given matrix, any chosen matrix. Capital A is a symmetric matrix plus a skew-symmetric matrix. You may get some doubt here 1 by 2 where suddenly it is not appearing, where it goes. 1 by 2 is a constant K. Any symmetric matrix is multiplied by its by any constant. Again it is a symmetric matrix. Skew-symmetric is also same. So you see the statement is proved well. Any square matrix can be expressed as the sum of symmetric and skew-symmetric. Will you agree? Yeah, that is the correct. Yeah.